All right, so welcome to this video. Why don't you pause, copy this down, and then press play. In this video, we're going to learn how to graph a rational function, putting together a bunch of things we already know how to do. So there's going to be nothing actually new here, just throwing everything together into one coherent whole. We're going to spend 2 days graphing rational functions. First day, we're going to have a function and graph it. Do a bit more of that on the second day of class. And then on the second day of class, we're also going to be given a graph, and we're going to try and create the rational function whose graph it is. So reverse the process, as it were. All right. These problems take a while. So this will be the only example in this video. I've got a rational function, one polynomial divided by another polynomial. And in this case, I've also been given the factorization of the numerator and the denominator. The numerator, we could certainly have factored that. The denominator would have been a lot trickier. It did not factor via grouping, so we would have had to have used some other techniques that we haven't covered in this class. Anyway, it's factored. What we are going to do is we are going to take this function and calculate the y-intercept, the end behavior, the domain, and that's going to help us learn where the holes or the vertical asymptotes are. X-intercepts, if there are any, and then maybe plot some additional points if we need to get a better sense of the graph. All right. Now, I'm going to start with the y-intercept and the end behavior because those use the unfactored. It's easiest to use the unfactored version of the function for the y-intercept and the end behavior. So, 1, y-intercept. Nothing surprising here. Set x equal to 0. Grind out y. So I'm going to plug 0 into my function for x. So I get a 0 squared plus a 0 minus a 2 on top. I'm using this unfactored version. A 0 cubed, a 6 times 0 squared, a 5 times 0, and a negative 12. So it looks like I get negative 2 over negative 12, which is the same as positive 1, 6. So that is my y-intercept. And I'm going to plot it right now over there. So hopefully you'll pause now and make your own graph. And by the way, I need some space on the negative side, more space on the negative side than the positive side, as it turns out. All right, so I need to plot at 1, 6. So let's just say that was y equals 1. And about 1, 6 on the y-axis would then be maybe, let's just say around here. Okay. All right, so I plot my y-intercept. Graph's got to go through there. 2, end behavior. This is where I'm letting x go to negative infinity and x go to positive infinity to see what happens with the y value of the function. Okay. All right, so let me do limit as x approaches negative infinity. And we've done problems like this. In fact, I think this is the content of your homework that you're currently working on. X cubed plus 6x squared plus 5x minus 12. So our standard technique for these, if x is going to infinity or negative infinity, is to grab the highest power of x in the denominator, that's an x cubed, and I'm going to multiply the denominator by 1 over x cubed. And whatever I do to the denominator, I've got to do the exact same thing to the numerator. So I'm going to multiply top and bottom by 1 over the highest power of x in the denominator. In this case, an x cubed. Okay. All right, so let's see what happens. Limit x approaches negative infinity. Well, x squared times x cubed. Both of the x's cancel from the x squared, leaving 1 behind in the denominator. And then there's a 1 left on top. X times x cubed. Well, x kills off one of the x's in the x cubed, leaving 2 behind. So I think that's a 1 over x squared. And there's a plus sign in between them. And then negative 2 times 1 over x cubed to be negative 2 over x cubed. Denominator, x cubed times 1 over x cubed. The x cubes cancel, leaving the 1 behind. 6x squared times x cubed. X squared kills 2 of the 3 x's downstairs, leaving 1 downstairs. The 6 times 1 is upstairs, so I think I have a 6 over x, positive sign. 5x times 1 over x cubed. X kills off 1 of the x's, leaving an x squared in the denominator, and 5 times 1 in the numerator. So I think I have a 5 over an x squared. And positive sign in between them, and then negative 12 over x cubed at the end. Okay, so I get that uglier looking thing, but now the really fun plug in a big number in the denominator makes life easier. So when I plug in a big negative number in any of these 5, 6 fractions, I'm going to have something finite divided by something enormous. Enormous and negative, but enormous. So 1 divided by enormous is really small. So small, it's just about 0. It's like 0.00001. So we'll just call it 0. Same story there. This was 1 over a large negative. This is going to be 1 over a large positive. But either way, we're getting a number close to 0, maybe a negative number close to 0, followed by a positive number close to 0, but they're both exceedingly close to 0. So we just call it 0. And then same story here, enormous number in the denominator, something small on top, that's another 0. Even subtraction if you like. 1, well, limit doesn't affect it because it's got no x's. And then all 3 of these fractions are zeros, just like they were up top, okay? So I get 0, 0, 0. So I think I get 0 over 1, which is 0. Right, so as my x values head off to negative infinity, way off to the left, my y values approach 0. So let's put that graph in there. So my end behavior way off to the left is, as x goes way off to the left, my y values get close to 0. So I think my graph's either got to do this, approach 0 from the left, or sorry, approach 0 from below, or I might approach y equals 0 from above, okay? All right, now let's do the limit as x approaches positive infinity, but I'll do it quickly because nothing much is going to change. Let's say I had x approaching positive infinity. I would still do the 1 over x cubed trick, so I'd still get to this next step, but I'd have positive infinity. And now, if I plug in a big positive number in these denominators, I'm still getting something finite, small, divided by something enormous. Those are still fractions that are equal to 0. So I'm still getting a 0, a 0, a 0, a 0, a 0, a 0, and a 1. So that step's still the same. And then after that, it's just been arithmetic. So as x approaches positive infinity, my y values will also approach 0, right? So in this case, the x going to negative and x going to positive infinity give us the exact same answer. It's not always true, so you always have to check both sides, both ends, but in this case it does. So where's my green marker? So as x heads way off to positive infinity, my y values again are approaching 0, either from above or from below. Now, I'm going to have to figure out, is it above or is it below? But we'll do that later on. I don't think I've got enough information to figure that out yet. All right, so the upshot of all this is that y equals 0 is a horizontal asymptote. Cool. And hopefully we've got that graph there. Okay. All right, well, let's zip over to the other side of the board and deal with the domain, poles of vertical asymptotes, x-intercepts, and maybe plot some additional points. All right, let me just list the function again. And this time, I'm just going to list the factored version because for the rest of the work, it's going to be the factored version that's easiest. Okay. I like it there. All right, so let me just do the domain. Okay, now in our factored version, there's no square roots, so that's not a trouble spot. The only other trouble spot we have is there's the denominator, and there are x values that could make the denominator equal to 0. So domain, it looks like the trouble spots, the x values I cannot allow, are x values like x equals 1 would make the first factor 0, and then 0 times anything is 0. So that gives me a 0 in the denominator. X equals -3 would make the second factor 0, and then multiplying anything by 0 keeps it at 0. So -3 is no good. And then x equals -4 is similarly no good, okay? So those are my 3 trouble spots, right? And I identify these because they're either going to be holes or vertical asymptotes, right? And I have to figure out which they are. So let's go up here and let's just start with x equals 1. I'm going to figure out what each one of them is by taking the limit as I approach the trouble spot. So if I take the limit as x approaches the first, well, not the first trouble spot, but the first in my list, x approaches 1, I'm going to use the factored version, x minus 1, x plus 2, x minus 1, x plus 3, x plus 4. Okay. Now, if I do direct substitution, I clearly get a 0 in the denominator, so I'm screwed. But good news, the x minus 1s. So direct substitution failed. So now I'm going to see if I can algebra the problem away. And it looks like I can because the x minus 1s cancel each other. And now if I do direct substitution, I don't get 0 in the denominator. So now I'm going to do direct sub. So I'm going to get 1 plus 2. I'm substituting in x equals 1, 1 plus 2 over 1 plus 3, 1 plus 4. So I get 3 on top. I get a 4 times a 5, so it's a 20 downstairs. Okay. So the limit as x approaches 1 exists. I was easily able to calculate it. It's a nice finite number. So that means we have a hole at x equals 1, y equals 3 over 20. And my graph approaches this hole from either side. That's what the limit has just told me. So it's not a vertical asymptote because the limit wasn't infinity or negative infinity. It was a nice finite number. So it must be a hole. So I'm going to plot that hole. All right, so here's 1. This was 1/6 and 3 over 20. I don't know, it's not too important. Is 3 over 20 bigger than 1/6? It's 0.15. No, it's a bit smaller than 1/6, but again, not important. 3 over 20 is not a very big number. It's close to the x-axis. So I'm going to put a hole there, okay? And the graph's gotta hit this hole from either side. So maybe I'll just put something like that in there, though I don't really know what the graph's looking like there yet, just that it runs through that hole and then I remove it. So I can't plot it at that hole. So I make an open circle. Great, so we figured out one of the trouble spots. Now I'm going to go for the limit as x approaches -3. And I might as well use the canceled version of this function because I would do that in the first step of this limit anyway to see if I can use direct substitution. So let's pretend I've already canceled the x minus 1s and just pick up this limit at the next step. All right, and though I canceled out the x minus 1s, that wasn't the problem for the limit as x approaching -3. The problem's at factor x plus 3. So I wasn't able to algebra it away. So if algebra fails, which means direct substitution's failing me, I got to go to a one-sided limits from the left and the right. Okay. So I'm going to approach -3 from the left. So this is like -3.001s of x plus 2, x plus 3, x plus 4. Okay. All right. And this is where I'm going to be sloppy and careful. I'm going to be careful at x plus 3 because that's what's giving me the 0 in the denominator. But at x plus 4 and at x plus 2, I'm going to use -3 instead of -3.001 because it's no major difference adding 2 to -3 versus to -3.001. And it's not giving me a 0 in the denominator in those two factors. So I replace x plus 2 with -3 plus 2. I replace x plus 4 with -3 plus 4. And then at x plus 3, I'm careful. So if I plug in a -3.001 for x and add 3, I'm left with -0.001. So I'm left with a small negative. Okay. All right, let's grind that out. So on top, I've got a -1. Downstairs, I've got a small negative times +1. So that's, well, it doesn't change anything. Small negative times +1 is still a small negative. And then -1 over small negative is big, and negative over negative is positive. So I think I get positive infinity coming out here. So as I approach -3 from the left, I'm zooming up to positive infinity. Let's put that in the graph. So there's -3, and as I approach from the left, I'm zooming up. So I think I've got this kind of a behavior, which I believe tells me at -3, I'm going to have a vertical asymptote. And I know what the graph's doing from the left. All right? Let's find the other side of a -3. So x approaches -3 from the right. I'm thinking like -2.9s. I'm jumping or using that factor canceled version of the function. I'm going to be sloppy with the x plus 2 and the x plus 4. So it's a -3 plus 2. a -3 plus 4, just like it was up above. And now a -2.99 plus 3, I think that's going to leave me with a positive 0.001, so a small positive, small pos. All right, so I get a -1 on top. Small positive times +1 is still small pos. -1 over small pos is big, negative. So I think I get negative infinity coming out there. If I'm getting too far ahead, just stop, write it down, rewind it, and let me talk you through it. All right, so I think as I approach -3 from the right, my y values are zooming down to negative infinity. So as I approach x equals -3 from the right, I'm zooming to y values that are big negatives. So definitely a vertical asymptote. X equals -3 is a vertical asymptote. And I know what the graph looks like on either side of it, okay? All right, now, last trouble spot was at -4. So I'm just gonna repeat this process with the limit as x approaches -4. So direct substitution fails. All right, and I can't cancel that x plus 4 away, so I've got to go to left and right. So if I approach -4 from the left, I'm like the -4.001s. I've got my x plus 2, I've got my x plus 3, my x plus 4. Ooh. So now I got to be careful at x plus 4 and sloppy at x plus 2 and x plus 3. Ooh, equals are getting tough. So I'm going to have a -4 plus 2 on top, a -4 plus 3 instead of x plus 3. And now -4.001 plus 4 is going to give me a -0.001. So I've got a small negative here. So small neg. Okay. So it looks like I've got a -2 on top. A -1 times a small negative would be a small positive. And -2 divided by a small positive will be a big negative, which I might call negative infinity. Okay. All right, so as I come up on -4 from the left, my y values are diving down. So approaching -4 from the left, my y values are heading down. So it's feeling like I'm going to have a vertical asymptote at -4 as well, diving down from the left. All right, from the right, x approaching -4 from the right, I'm thinking like my -3.9s. X plus 2, x plus 3, x plus 4, sloppy with the x plus 2, x is -4, x plus 3, I can be sloppy, and then the x plus 4 factor, I'm careful. So -3.999 plus 4, I think gives me a positive 0.001, so a small positive number. So I think I get a -2 on top. I have a -1 times a small positive, that's a small negative. And -2 over small negative is big, and it's positive, so I get positive infinity, okay? So approaching -4 from the right, my y values are zooming up. So as I approach -4 from the right, my y values are zooming up. And it's getting crowded between -3 and 4. But I've got that kind of behavior just to the right of -4. Okay, so this tells me that x equals -4 is a vertical asymptote as well. So I had 2 vertical asymptotes and 1 hole. Okay, all right, well, let's see if we can complete our graph now. All right, and let me get rid of this just because it's unattractive. All right, so I've got to make a coherent picture out of this. Oh, wait a minute. I've got one last thing to do. X-intercepts. My bad. So obviously down here, I now want to calculate x-intercepts. So for x-intercepts, I set f of x equal to 0 and solve for x. It's what we've been doing all semester with x-intercepts, okay? I'm still going to use the factored version and not the canceled version. I want the full factored version. So x minus 1, x plus 2, x minus 1, x plus 3, x plus 4. So there's my function. I'm going to set it equal to 0, and I'm going to try and solve for x. And that looks horrific, okay? But it simplifies really nicely. There's only one way a fraction can equal 0, and that's if the top of the fraction, the numerator, is 0, okay? So if I have a fraction equal to 0, it must be the case that the numerator is equal to 0. So what I'm saying is a over b equals 0 means a equals 0. And here's why. Multiply both sides by b. B's cancel, leaving an a on the left, and 0 times b is still 0 on the right. Okay? So the only way a fraction equals 0 is if the numerator is 0. Let me erase that. I can leave it up for a minute. All right. So the only way x minus 1 times x plus 2 is 0 is, well, either the x minus 1 is 0, or the x minus 2 is x plus 2 is 0, and that would lead to an x value of -2. Okay. So according to the algebra, the x-intercepts are at 1 and -2. But remember, x equals 1 is not even in the domain of the function. All right. So x equals 1 is a false x-intercept, not in domain. So the only x-intercept is x equals -2. All right. So let me plot that point at -2. I am crossing the x-axis. All right. And now I've got to fill in the in-betweens. Okay. So let's start between -3 and -4, two vertical asymptotes. And inside, as I move out, I'm zooming up on both sides. And I'm not allowed to cross the x-axis. Right? So I think at some stage, I've got to sort of create this sort of parabolic looking thing. Now, how far down it goes, I'm not sure. I could plot like -3.5 and get a sense of that. Okay, but since I'm just after the shape, that's good enough for me. I know it goes down and it doesn't cross the x-axis, and then it goes back up. Okay. All right, let's look to the left of -4. I've got to hit that vertical asymptote behavior, and I've got to hit one of these two end behaviors, and I'm not allowed to cross the x-axis because I have no x-intercepts here. So I think there's no way I can reach this end behavior that's above the x-axis without having crossed the x-axis. So I'm going to erase that. It's not an option, and just sort of smooth that out. Boom, boom. Okay. All right. And then the other side of -3, I've got to be zooming down, but then I've got to hit my x-intercept, my y-intercept, my hole, and one of these two end behaviors. And the only place I'm allowed to cross the x-axis is at -2. So I think it looks like I'm going to cross the x-axis and stay above it. And there's no place here for me to cross the x-axis again. So I think this lower end behavior option is not possible. So zoom, and then sort of flattening out along the x-axis. Okay. All right. So it's just that quick and easy. Cool.